In our third lab, we're going to be making aspirin. So one of the important reactions we're going to look at this semester is the reaction between an alcohol plus a carboxylic acid. So they will react together to form an ester, and the other product is water. So this can be done under acidic conditions and with some heat. So when we go to do this in the lab, then what happens is the water, one of the products there, can actually result in the hydrolysis of the ester. So we get the reverse reaction to get the alcohol and the carboxylic acid. So this then decreases the yield of the ester. So in the lab, one way to improve the yield of the ester, so rather than using the carboxylic acid, is to use what's called an acid anhydride. So this is two molecules of the carboxylic acid that have joined together and lost a molecule of water. So that anhydride means without water. So in the lab we can use an alcohol plus this, effectively a activated carboxylic acid. So again, under acidic conditions, heat it up, we get an ester, but this time the other product is a carboxylic acid. So that's not going to decrease the yield of the ester. So that's what we're going to do in this aspirin synthesis. So we can start off with salicylic acid. So this is a compound that is extracted from the bark of willow trees, and we can see in its structure, so it has a benzene ring, it has a carboxylic acid functional group, and it has this hydroxyl group attached to the benzene ring, so it is a phenol. So this is the alcohol part of this reaction, so this OH group here attached to the benzene ring. So it's going to react with acetic anhydride, so this is the anhydride of acetic acid. So acetic acid has 2 carbons there, another 2 carbons, so 4 carbons in total. So we're going to heat this up, we're going to use a little bit of sulfuric acid, and this will acetylate, so to make an ester at this oxygen here. So we've got this R, double bond O, O, R. So this is an ester functional group. So this is called acetyl salicylic acid. So we still have that carboxylic acid group, but now we've got this ester functional group where that alcohol was before. And so then our other product here is acetic acid. So what we've done is to add 2 carbons to the salicylic acid in order to make acetyl salicylic acid, and then we've got the 2 carbons there in acetic anhydride. So they were the 4 carbons from in acetic acid, so they were the 4 carbons from acetic anhydride. The other task you'll have in this lab is to make some molecular models and then to draw them. So with the more complicated ones, such as butane, then I'm asking you to draw them from 2 different perspectives. So a bit like if you're drawing a house from the front and from the side. So I find the simplest way to draw them, and that conveys the most information, are these 2 projections here. So the natter projection, which we have a single lines there for all the carbons on that backbone, and then the hydrogens at the end. And then there are wedges for the hydrogens coming out towards us, and dashes for the hydrogens going away from us. So we know that with the sp3 carbon, so where it has 4 single bonds attached to it, then all the bond angles are 109 degrees. So I don't want you drawing 90-degree bond angles in this. So with the natter projection, and I have here this molecule of butane, and if I was to rotate that slightly, so we can see we've got these, so the terminal hydrogen and the 4 carbons, and then the terminal hydrogen, they're all in the same plane. And then we would have hydrogens coming out towards us, which would be the wedges, and then the hydrogens at the back, so we would draw dashes to those. So that's a bit like looking at the molecule from the side. So that's the natter projection there. Wedges coming out towards us, dashes going away. With the Newman projection, so this is if we were to take another perspective of the molecule. So this time, I've rotated the molecule, and if we look down a central carbon-carbon bond, so we've got the 4 carbons there, it's still butane, just the molecules rotated. And so if I was to pause this, then we have this carbon-carbon bond that we look down. So with the front carbon, it has hydrogen pointing down to the left, down to the right, and then it has a methyl group up to the top. We can't see that back carbon because it's behind the front carbon, but off that back carbon there would be hydrogen pointing up to the right, up to the left, and then a methyl group pointing down. So that's what's shown here in this Newman projection. So we've got from that front carbon, you can see these full lines because we can see all of that carbon to hydrogen bond or carbon to methyl bond. Off the back carbon, we can't see the back carbon, but then we have these half lines here because these are bonds coming off the back carbon. So you can use that Newman projection to draw larger